Okay, this is the beginning of chapter 8. So we're doing sections 1, 2, and 3. And chapter 8 is all about solution chemistry. And solution chemistry is really, really dependent upon all of the attractive forces that we talked about last time. So you have to remember that like dissolves like. So things that are polar dissolve in substances that are polar. Substances that are non-polar won't dissolve in substances that are polar and will dissolve in substances that are non-polar. So remember that water is polar. So most organic substances that we talk about, organic meaning carbons and hydrogens, right? They're non-polar, so they won't dissolve in water. And we talk about water a lot because water is our universal solvent, right? It's usually, our solvent is usually water. So whenever we talk about dissolving one substance into another, if I take salt and I dissolve it in water, I'm usually putting a little bit of salt in a lot of water. So whatever I have a lot of is the solvent, and whatever I have a little bit of is the solute. So let's try to apply some of that stuff. So identify the solute and solvent in the solutions composed of the following. Heliox, a breathing gas that is 79% helium, 21% O2 for patients who have difficulty breathing. So we want to know which one's solvent and which one is solute. So let's put a little table. We'll go down here. Solute, solvent, and we'll do that for A, B, and C. Okay, so my solute is the one that is the lowest amount. So this would be O2. My solvent would be the helium. So this is a kind of cool, this is actually a side note, this is a kind of cool thing that they can actually do for people who struggle to breathe. Because in normal air, you have about 78% nitrogen and you have about 21% oxygen, and you have like 0.0005% helium, right? So normally we don't have very much helium inside of the air that we breathe. But here we're basically replacing the nitrogen with helium. And if you look at the periodic table, look at the mass of nitrogen versus the mass of helium. Helium is much, 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 much lighter. It's less dense. The air that they breathe in this heliox is much less dense, and so it's much easier for them to inhale and take a deep breath. So it's kind of a cool thing. Okay, children's Tylenol, which is an oral suspension that contains 160 milligrams of acetaminophen per 5 grams of water. So what am I putting a little bit of? I'm putting in acetaminophen. I'm never going to fit that. Acetaminophen. And then my solvent in this case would be water. So whatever's the most is the solvent. Then I don't even remember. It's an organic herbal remedy thing containing a small amount of an herbal remedy dissolved in alcohol. So whatever we're putting into the alcohol is the solvent, right? And then the solute is whatever the herbal remedy is, right? So you're just looking at what's the most and what's the least. Solvent is the most, solute is the least. Okay, that was pretty easy. So the next one, we're going to identify some different combinations of things. So we have solutions, we have colloids, and then we have suspensions. And so I thought it might be good to pause here and kind of give some examples of each and kind of describe each of them. So if we have a solution, how do I know it's a solution? Well, if I have a solution, my substance completely dissolved. So the solution is transparent, right? My salt going into water, I can see through salt water. So that's transparent. Sugar water, I can see through sugar water. That is transparent. Therefore, it's a solution. Another different kind of example, right? This is salt water, sugar water. Coffee is another example. If you hold it up to the light and you have it in a clear cup, you can actually see through it. Now, this is before you add, your creamer to it, but when you just fresh brew coffee, you can actually see through it. That's how you can tell it's a solution. If you can see through it, it's a solution. The next one is a colloid. This one has substances that do not dissolve. So this contains substances that do not dissolve, right? So big things like if you have proteins, you got fats, right? It's relatively small particle size. Like you can't take out a molecule of a protein, right? You can't pick it out, but they're so big that they're not actually going to dissolve. And so they're smaller particle size, right? So they're smaller particle. And so the cool thing about colloids is that because the particles aren't too big, that they actually don't settle. So this does not settle. So if you left it out on the counter, it would still stay homogeneous throughout. So a good example of this is like milk or cream. If you left your milk in the fridge, do you have to shake your milk before you put it on your cereal? No, there's no layers in milk, right? So you never will see layers in a colloid, but it's not see-through. So that's how you can tell the difference between a solution and a colloid. So let's talk about some things that are similar between solutions and colloids. They're homogeneous, right? We can't pick out individual things. So they are both homogeneous, Geneous, genius solutions, right? So by definition, then they must be mixtures, right? We're mixing two things together. Another word for homogeneous might be uniform, right? And they're not going to separate over time. So will not separate over time. So if you leave it out on the counter, if you left out salt water, would you come back and you'd see a layer of salt? No, right? Same thing with milk. I mean, you got to keep it cold or it'll curdle, but that's a different reaction, right? So the milk's not going to separate just sitting in the fridge. Okay, so how are those things related to a suspension? A suspension is a whole lot like a colloid, but it has very large particle size. So this will separate. This is the only one that will separate if you leave it out, right? So one standing, if you leave it out on the counter. So a lot of times what you're going to see examples of this is medicine that you'll prescribe to children, right? So children's oral medicine. So if you're going to give them like amoxicillin, right, they're going to have to mix it with water, and they usually mix it with some flavoring for the kids. And it'll always say on the bottle, shake before dispensing. And that's because it's a suspension and the particle sizes are really big in there. And they're so big that gravity will actually pull them down and they'll settle over time. Another example is blood, right? The red blood cells will settle, right? Blood is mainly water, but it has red blood cells, and those red blood cells will basically sink over time. Muddy water is another example, right? Okay, so now that we know this stuff, let's see if we can come up here and do 8.4. Identify the following as solutions or colloids. 5% albumin a protein IV replacement fluid. So what we're saying here is that we have a protein inside of a fluid. And that fluid, if you're giving it in an IV, right? What fluid does that have to be? That has to be water. Has to be. So if you're giving it as an IV solution and you're putting a protein in there, where do we see down here that we have, let's see if I used to could do a laser pointer. Let's see. So where do I have a proteins here in my colloid? I have proteins, they're smaller size. So they're going to stay in solution. But what we'll see is that that is a colloid, right? It's not going to settle. So it must be a colloid. The electrolyte replacement IV fluid lactated Ringer's solution. So if we have electrolytes, right? So if you're like, you get really, really dehydrated, they give you not just an IV of just water, right? But they give you an IV that has electrolytes. What are electrolytes? Electrolytes are basically ions. And so if you had something like NaCl, what happens when you put NaCl into water? When you put NaCl into water, it turns into a sodium ion plus a chloride ion. So these are those electrolytes, the charged particles. So if we just have ions inside of water, then we have a solution, right? D5W, a 5% dextrose IV fluid. What is dextrose? Dextrose is just a sugar, and the IV is water. So that also has to be a solution. Okay, so just kind of get to know this table and be able to think about it. Okay, so now we're going to talk about different things that can happen to solutions. So I know you probably don't remember this, but as a kid, I remember that we would put, when we would make Kool-Aid, you had to put like regular sugar into Kool-Aid, and it was like cups. You put the little flavoring packet in, and nowadays it comes with artificial sweetener in there. So it tastes sweet, but you're not putting scoop after scoop after scoop of sugar. But I remember making it as a kid. You had to put in the real sugar, and as you would stir it, you could hear the grittiness of it, and you had to stir it for quite a while until all that sugar would go into solution. Well, if you kept adding sugar and adding sugar and adding sugar and adding sugar, eventually you would add so much sugar that that solution would be saturated with the sugar. And eventually that sugar just wouldn't dissolve anymore. And that's when you get to that saturated solution. And technically, right, if you had like, you had your little beaker, your pitcher, right, and you're putting salt in and putting salt in, you would have crystals, right, of not salt, sugar, right? And then you'd have some that would go in and be dissolved. And at the same time, you have some particles that are dissolving, and then you have some particles that are recrystallizing. So you actually don't have the same particles staying as crystals. It kind of cycles. And so you just have the same basically amount of sugar that's in solution and the same amount of sugar that's not going into solution, that's still staying a crystal. So when we talk about that, you just have to be able to recognize a saturated solution. So for 8.6a, we have a piece of rock salt that does not change in size when it's added to a salt solution. So we basically have so much salt in the solution to start with that we're putting a little bit more salt, a rock salt in there, and that rock salt doesn't change size. So some of it is dissolving, some of it's crystallizing. So that's an example. Yes, that is an example of a saturated solution. A teaspoon of honey that dissolves in hot tea. If it dissolves completely, that solution is not saturated. So we would say no there. Okay, so when we talk about what happens in terms of how can we change the solubility of something. I want you to think about two things, and I'm gonna copy these two things, these two little statements over here, and we're gonna take them and we're gonna use them down here. So we're gonna copy, and I'm gonna put them. We don't have room. Yeah, we could do it together. Okay, add page. Okay, so we're just kind of taking a little side trip real quick. Okay, there are two kind of things that you have to worry about being able to change the solubility. Do you have a solid inside of a liquid, or do you have a gas inside of a liquid? So whenever we talk about a solid inside of a liquid, I want you to think about your grandmother's old-fashioned tea. Old-fashioned tea, right? My grandmother used to make this. I remember being in her kitchen, and she would get out the tea bags, and she would, put her kettle on the stove, and she would boil the water, and she would pour this hot water over the tea bags, right? And it was really important that she would let those tea bags steep, right, for quite a while. And when she pulled those tea bags out, that water was still hot. And so she was like, you have to put in the sugar while the tea is still hot. And I never really understood why, but it's all about solubility. So in order to get a solid to go into a liquid, to get it to dissolve, what you're going to do is you're going to increase the temperature to increase the solubility. So what we're doing here is we're keeping our tea hot, and we're adding sugar, right? Have you ever seen how much sugar was added to those old-time tea, like old-fashioned sweet iced tea? You couldn't add the sugar into the cold tea because it would be too gritty, like it wouldn't want to go into solution. So what do? You add the sugar. You add the sugar in while it's hot. Then you let it cool, refrigerate, ice it, whatever. And then you make iced tea, right? Iced tea. So that's what I want you to kind of think about when you think about solid inside of a liquid. And that's how you'll remember, if you increase the temperature, increase the solubility. For gas inside of a liquid, my favorite gas inside of a liquid, and I am not promoting any brand in any way, shape, or form, but I'll admit to it that I love a Diet Coke. Love a Diet Coke. So when you think about a Diet Coke, if you've ever opened any kind of soda, right? When you pop that top and you hear that psh, right? That's a little bit of the gas escaping out. What gas is inside of a Diet Coke? It's a carbonated drink, so it's got to be something with carbon in it. It's actually carbon dioxide and most of a Diet Coke, most of any liquid that we drink is water, right? And it's got some flavorings and whatever, but CO2 is my gas and water is my liquid, right? So what happens if, let's just say, I'm in my office and I'm sitting down and I pop that Diet Coke open, and I take that first sip and it's so nice and bubbly on your tongue, right? And then I get somebody come in my office and, we're going to work some problems. And I'm so excited. I get to work some problems with y'all, and next thing you know, an hour has passed and I've totally forgotten about my Diet Coke. I left it out on the counter on my desk and it got warm, and I go to take a sip of it. How does it taste after an hour of sitting out on the counter? It tastes kind of flat, right? So if I leave it at room temperature, at room temp, my Coke goes flat, FLA, flat. And I'm so sad, right? Well, why? What's up with that? Well, what should I have done? When somebody walked in my office, I should have put my Diet Coke in the fridge, because if I put it in the refrigerator, then An hour later, I open the fridge again and I take another sip, and it's still carbonated. And I'm a very happy camper, right? So what can we learn from this? Well, if I increase the temperature, so if I go from the refrigerator to room temperature, my temperature is going up. I'm going to decrease solubility. So what happened to me as I left my Diet Coke out at room temperature is that because the temperature increased, the amount of gas that's dissolved inside of my liquid decreases because the gas escapes right out of the top of the can. And so now it tastes flat. Oh, so sad, right? So remember those two things when you're talking about solubility of whether it's a solid or a gas in liquid, and you'll be able to answer all the questions. So let's try some. If the temperature of a solution decreases, okay, so my temperature decreases, what happens to the solubility of a gaseous solid? So all of this, you can assume it's a liquid. So here we're going a gas into 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 a liquid, right? Gas into a liquid. So what's going to happen? If I decrease the temperature, are we going to become more soluble or less soluble? We're going to become more soluble. So this is an increase, right? This is my Diet Coke example, right? Okay, the next one. If the temperature of a solution decreases, so if my temperature decreases, the solubility of a solid solute. So this is my Coke, not my Coke. This is my tea example. I'm making some nice tea. So the solubility of a solid solute will go up or down. So remember your rule. The solubility of this solid will go down. So this will decrease, right? So if I brewed my tea, right? And then I went and did something else and I came back and my tea was cold and I tried to put my ton of sugar into that tea, it's not going to go in. All right. If the pressure above a solution decreases, this one's a little different. Pressure. The solubility of the gaseous solute will do what? Let's think about this. This is also the Diet Coke. The Diet Coke example. Have you ever dented a Diet Coke? Have you ever, any kind of soda, like you dropped it on the ground and it dented and you were like, oh my God, what should I do? You don't open it, right? Because if you open it right away, it's going to fizz out everywhere. Why? What did you do? When you dented that can, you actually reduced the amount of volume in that can. And so you actually increase the pressure. And so when you pop that top and you finally release the pressure, that Diet Coke's going everywhere, right? But this is how they package sodas. They put the gas in with the liquid and they increase the pressure. And so the gas will go into the liquid because it's high pressure. So if you increase the pressure, you're going to increase the solubility of a gas, right? So what's going to happen? If the pressure above a solution decreases, so here my pressure is dropping, so then my solubility is also going to drop. So this is a decrease. So it's also Diet Coke. So anything you can relate to, so it's the South, you can do it with tea and Diet Coke. All right. So explain what would happen in the following situations in terms of solubility. Okay. Fish die in a lake that is heated with water from a power plant cooling tower. Ooh. So I have a lake, right? I have some water and that water is being heated. What do fish need to do to survive? Just like us. They have to breathe, right? They breathe by passing water over their gills and then extracting out the gaseous O2 that's inside of water, that's dissolved inside of water. So what happens in A is you are increasing the temperature, which means you are decreasing the solubility of O2, of oxygen gas, this is oxygen gas, in the lake water. And that's why they're dying. Poor fish. Oh my gosh. I'll draw them a sad face too. They're dying. That's terrible. And that happens all the time, unfortunately. Okay, B, crystals form in a jar of honey that has been sitting for several months. So a lot of times when you buy a jar of honey, right, it's perfectly sealed. But once you open it and start using it, it's no longer a perfect seal. So as they're sitting for several months, what's happening? Water's evaporating. As water evaporates, what happens to the concentration of the sugar particles inside of water? You're actually going to increase the concentration, T-R-A-T-I-O-N, concentration of the sugar in the honey. And you'll get to a point where it's a saturated solution. And once we're saturated, what are we going to get? We're going to get sugar crystals crystallizing, sugar particles crystallizing. Sugar will crystallize. Okay. All right, C, a person receives oxygen through a breathing device. So let's say they're on a ventilator. How does a ventilator work? How are they getting that oxygen? All you're doing here is increasing the pressure of oxygen that's delivered to the lungs. So usually you're at 1 atm of pressure, that's atmospheric pressure. But if you're on a ventilator, that's going to be higher. So you're going to increase pressure of the O2 that's delivered to the lungs, right? And so then it allows for more oxygen to become dissolved in the blood, because we know if we increase pressure, just like up here, where we increase the pressure above our solution, then our gas went into solution, right? So same thing here. We increase pressure of O2 delivered to the lungs, so you have more O2 dissolved inside of the blood of the patient, right? All right, let's see. Okay, a hyperbaric chamber. Oh, this is cool. So you have hyperbaric chambers that are 100% oxygen. We typically breathe 20%. That's what's normally in the air. So if you have a patient who comes in who's had carbon monoxide poisoning, we know that carbon monoxide actually binds to our red blood cells more tightly than O2. So how do you treat somebody who's got carbon monoxide poisoning? Basically, their red blood cells that have the hemoglobin don't want to give up the carbon monoxide. So here, if you are increasing the percent of O2, that's basically you're increasing the pressure, the partial pressure, which is an increase in pressure of O2, right? You went from only 20% to now being 100%. So you've increased the pressure. You have more O2 there. So more O2 will dissolve in the blood, right? And then eventually that's going to be used, because you're going to exchange it out. Eventually you're going to exchange it out. All in the blood, and CO will be replaced by O2. And we need O2. We don't want CO, which is carbon monoxide. Okay. So next, we have to talk about, when we make solutions, what's going to happen to the particles when we put them into solution. And there's kind of a couple of different possibilities. And so I kind of want to talk about this before we do some problems. So solids, when we put a solid into a liquid, we're making a solution. So solids that dissolve in solution, may or may not dissociate. So what you're going to notice here is that there's a difference between the word dissolve and disassociate. Those are two different things, and we have to be very careful about it. If something dissolves, that means we took a solid, we put it into a liquid, and we made a homogeneous solution that we can see through, right? It's a solution. So it dissolved. We can see right through it. Sometimes that solid is going to disassociate, which means it's going to split up into separate ions. So I want to use the example of salt first. What is salt? NaCl. So if salt disassociates, which it does, when we put it into water, it's going to make the sodium ion and the chloride ion. So this is an example of disassociation. Sugar, on the other hand, sugar is just, right, C6H12O6. If I take that solid, and you could do solid here, and these, if you dissolve them in water, you put AQ. If I take that and I put it into water, so a lot of times we write water like that. If I put it into water, I started with a solid, put it into water, what's going to happen to that sugar? A whole lot of nothing. The hydroxyls are going to interact with the water and hydrogen bonds, but it's not going to break up the way sodium chloride broke up. I'm still going to have C6H12O6. That's not going to change. It's just going to be aqueous. That's it. So sugar does not disassociate, does not disassociate. Does not disassociate, whereas salt does. So when we talk about these different things, maybe I can move this up just a little bit. Getting a little crowded here. Okay, so when we talk about these things, what we also need to be able to talk about is using scientific terms. So we talk about them in terms of being electrolytes. I know that you've seen Gatorade, and it's like, oh, we have all these electrolytes in them. But what's really an electrolyte? An electrolyte is an ion, right? So you have things that are strong electrolytes, weak electrolytes, and non-electrolytes. If you have something that is a strong electrolyte, is it going to dissolve? Yes, 100% it's going to dissolve. But how about disassociate? A strong electrolyte will 100% disassociate. So it'll turn into all ions. A weak electrolyte, it is going to dissolve 100%. It's going to dissolve. Is it going to disassociate? Partially. Not completely. So only some of it is going to disassociate into ions. Then you have things that are non-electrolytes. Non-electrolytes, oh, they got dissolving, but they're not going to form ions. So do they disassociate? 0%. Never. Never. So our example of a non-electrolyte is sugar. Our example of a strong electrolyte is sodium chloride. And then there are lots of things in between. Okay, so now that we know that, let's predict what will happen. If we have sodium sulfate, and we're given a chemical formula, a strong electrolyte, what's going to happen? Well, if it's a strong electrolyte, let's talk about its disassociation. If we have something that's a strong electrolyte, what is it going to do? How much of it is going to disassociate? All of it. All of it's going to disassociate. So we say this is it will fully disassociate. If we have ethyl alcohol, you notice it's a lot like sugar. It's got carbons, hydrogens, and then a hydroxyl, right? It's not going to disassociate. It's going to dissolve, yes, but will it dissociate? No. And that's why I see this non-electrolyte. So this was a not, it will not dissociate. Okay, and then hypochlorous acid, HClO, a weak electrolyte. So this one, when I put it into solution, if it's a weak electrolyte, that means weak electrolyte here, it's going to partially dissociate. And the way that it partially dissociates is this hydrogen comes off as an H plus and you get ClO minus. So those are the two pieces that it turns into. But only some of them break up. Most of them stay together. Okay, so now we're going to put some stuff into solution and we're going to see what happens. So the first one, A, we're going to take sodium sulfate, Na2SO4, and we're starting as a solid. And we're told this is a strong electrolyte. So we're going to put in a single arrow. If 100% of it goes, I'm going to put a single-sided arrow because all the reactants are going to products. So we're going to put water on that arrow and we're going to disassociate it. Well, a lot of times strong electrolytes are ionic compounds. So I need to separate my ionic compounds. So what two things do I have? I have a sodium ion and I have an SO4 ion. So what you need to do is you need to look at the periodic table, find sodium. Sodium is in that first column, so it's going to carry a charge of +1. I need to move these a little bit farther apart. Okay. Then SO4 is a polyatomic ion. So you go to your polyatomic ion chart and you go look for the charge. It's 2-. When we put them in water and they disassociate, now we call them aqueous. So instead of being solids, now they're aqueous. So the last thing that we have to do is we have to worry about balancing these chemical equations. Over here, I have I have 2 sodiums. That's a little two sodiums. Over here, I only have 1. So how do I balance my sodium? Just put a 2. That's easy. Over here, I do this. I have 1 SO4 molecule. I have 1 SO4 molecule. So they're balanced. You could do the sulfurs individually and the oxygens individually, but because they always stay together, you don't have to do that. So now I have a balanced chemical equation. And be careful when you're doing this on the homework and make sure you put in these states of matter, right? The states of matter could be a solid, could be a liquid, could be a gas, or could be dissolved in water, in which case it would be aqueous. Those are your different states. Okay. B, ethyl alcohol, CH3, CH2OH. And this is a liquid. It's starting out as a liquid, and it's a non-electrolyte. Well, if I put this non-electrolyte into water, it's not really going to change. The substance itself is not going to change. CH3, CH2OH. It's just going to be in water. So we put aqueous and we're done. It's got to be the easiest equation. Now, do you have to balance it? Yes, but it's balanced. Beautiful, right? Okay, hypochlorous acid, HClO, starts out as aqueous. This is a weak electrolyte. If it's a weak electrolyte, that means some of it is going to turn into products, but not all of it. And so what we do is we do this as a double-sided arrow, and we still say it's going to happen in water. And what's going to dissociate? Remember when we said something's an acid? It is going to give up a proton, and we represent that proton as H plus. So that H plus is aqueous. Now what's left? If I take away a hydrogen, but it's not just a hydrogen, it's a hydrogen carrying a positive charge. So if it was neutral before and I take away a hydrogen with that positive charge, what's left? Well, what's left is my ClO, and that's carrying a negative charge because it was neutral before. I lost a positive, so now it's carrying that negative charge, but it is in water, so it's aqueous. And now we have to double check, are we balanced? And yes, we are. Okay. For the following ionic compounds, these are all ionic compounds, write a balanced equation for their hydration in water. So all you're doing is adding ionic compounds to water. So let's do the first one. FeCl3. So if it's an ionic compound, we're saying it's a solid, and we're going to put it into water, and what's going to happen? I'm going to separate the two. So just like finding the charge of things, right? We had to reverse crossover. It's the same kind of deal. So now Fe, what's the charge? Well, if I had 3 here and it crosses, this becomes a +3, and a 1 here becomes a -1. And we know chlorine is a -1, so that's good. Okay, so let me kind of erase that. Okay, so my Fe is a 3+, and it is aqueous, plus I have Cl-, and so my Cl- is also aqueous. Now I have to worry about balancing my chemical equations. I have 1 iron, 3 chlorines, 1 chlorine. So what do I do to balance it? I put a 3. Okay, and we're balanced. Pretty nice. All right, let's see. B, NaHCO3. So this is a solid. We're putting it in water, just like we did before. And what are we going to get? Well, HCO3, this portion right here, that's a polyatomic ion. And so sodium is going to be one piece, and the HCO3 is going to be another piece. H2O. Okay, so what am I going to make? I'm going to make Na+, aqueous, plus, and then what's left is HCO3-, and that's aqueous. So always go double check your charges. Double check your charges. All right, am I balanced? 1 sodium, 1 HCO3, 1 HCO3. Okay, so yes, we are balanced. Okay, so let's do C. What do we got for C? K2SO4. So it's our solid, putting it in water. So now what's going to happen to it? Well, K is one part and SO4 is another part. So I'm going to get my potassium ion, and we know that's a +1, and that is aqueous. Plus, we're going to get SO4. That's going to carry a charge. So you look on your polyatomic ion chart. That's 2-, and that is aqueous. Then we have to look at balancing. 2 potassium, 1. Ooh, not good. Got to put a 2 there. Okay, and then 1 SO4, 1 SO4. So we are good. Oop, get rid of all this and just leave the 2. Right? All right, then our last one, which we'll kind of squeeze in, I guess. All right, so we have CaNO3, 2. So we're gonna, it's aqueous. So we're gonna put it into water. Okay, now I'm just gonna draw my products at the bottom. So what am I gonna make? I'm gonna make Ca is gonna be one part of it, and NO3 is gonna be another part of it. So what's my charge on calcium? You should know that's a +2. Then NO3 on your polyatomic ion, look it up, it's a -1. They're both aqueous. We're going to add them together. I need a little bit more space. And we need to check to make sure that we are balanced. So 1 calcium, 1 calcium. 2, see all of this has a 2 on the outside. We have 2 NO3 molecules, but I only have 1 here. So I'm going to have to put a 2 right there. Now I am balanced. So just the more practice you do with those, the better. All right, when we give our patients any kind of an IV, things like that, it's really, 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 really important that we give them this about the same concentration of ions inside of their bloodstream as what's in the IV bag. And so the charge of what you give someone is super, super, super important. And when we talk about any kind of ion, if you, let's say we compare potassium and magnesium, a potassium ion is carrying a +1 charge. So a +1 charge is going to have an equivalence of 1. Why does it have an equivalence of 1? Because it's carrying a +1 for every 1 ion of potassium. I have a charge of +1. But what if I had magnesium? If I had magnesium, that's a 2+. For every molecule of Mg2+, I'm giving my patient 2 positive charges. So we call that 2 equivalents of Mg2+, right? The 2 comes from the charge. And this is really, really, really important because all of our body cells work on electrical energy, which is just charged molecules moving inside and out of cells. So if you mess up the charge, you could like kill someone. So knowing this is super, super important. So let's do the problem that we were supposed to do, kind of erase this stuff. Okay. So how many equivalents of Mg2+ are present in a solution that contains 2.5 moles of Mg2+? What are you starting out with? 2.50 moles of Mg2+. What is my goal? How many equivalents of Mg2+ do I have, right? That's my goal. So put what you're going to start with, 2.50 moles of Mg2+. Make sure you put all of those units and all of that information. So now it's just, guess what? Your favorite thing ever, dimensional analysis. Whatever you want to get rid of, moles of Mg2+. Now I'm going to give that into equivalents. So just like if you have 1 mole of K+, you get 1 equivalent of Mg+. So there's equivalents. But we have to look at those equivalents in terms of charge. So that ratio is going to be due to the charge. So you have 2 here. You always put the 2 with the equivalents. So if I have 1 mole of Mg2+, basically, how many charges do I have? Well, I really have like 2 moles of charges because each magnesium is carrying a charge of +2. So that's why the 2 has to go with the equivalents. So what am I going to make? 2.5 times 2 gives me 5. So I have 5 equivalent charges of Mg2+. Okay. All right. Here we go. Oh, this is interesting. Okay, so you're going to give patients an IV. And a lot of times when you give them IVs, you give them a couple of different things in the IV. You give them sugar and you give them ions because a lot of times they're dehydrated, they haven't eaten, right? All of those different things. So you're giving someone a 5% dextrose IV fluid that contains 35 milli equivalents. That's what the M is, milli equivalents of potassium per liter of solution. If a patient receives 235 milliliters of the IV solution, how many moles of K+ were delivered? This is my goal. So what am I going to start out with? I'm going to start out with 235 milliliters of that IV solution. So let me put that. I'm going to start out with 235 milliliters of my solution. Okay. Guess what we're doing? Woohoo! Dimensional analysis, right? So I'm going to start out with milliliters delivered, and I'm going to end up in hopefully moles of K plus. Okay. So if I want to get rid of milliliters, how am I going to do that? What am I going to do? Well, really what I'm saying is I'm going to take 235 milliliters of this solution. So in that amount, I want to know how many equivalents are there. So where else do I see a volume? Ooh, right here. I get 35 milli equivalents per liter. So I want to go from milliliters, to liters? No, I can't do that. But what I could do is convert milliliters to liters and then put liters on the bottom. And I know I have 35 milli equivalents per 1 liter, right? But I got to fill in my previous one. So to cancel out milliliters, I know I have 1,000 milliliters in 1 liter. So now I know my milliliters cancel, my liters cancel. I'm in milli equivalents, but is that what I want to be in? Nope, that's not what I want to be in. I want to be in moles, right? Okay, so I know I'm going to have to get rid of milli equivalents. So where do I go from there? Well, I got to go to equivalents, right? Because I want to know how many moles, right? So I know a relationship between equivalents and moles. That's what I did right here. So I'm going to do that same thing down here. So I said, okay, 35 milli equivalents. I got to get rid of milli equivalents. So I know milli means 1,000. So I have 1,000 milli equivalents in 1 equivalent, right? So my milli equivalents cancels. Then I want to get rid of equivalents. So in order to get rid of equivalents, where am I going? I'm going in 1 equivalent of what substance is this? Of K plus. How many moles of K plus am I going to have? Ooh, I did that without telling y'all. I jumped ahead the gun. Okay, so milli equivalents to moles. What's my relationship? I know for whatever substance, I have 1 mole of that substance. So say substance X has some charge is equal to the intensity of that charge. That's how many equivalents I have. So if I have something that in this case is K plus, so then I have 1 mole of K plus, I have 1 equivalent of K plus. So I can plug that in and I can say, okay, in 1 mole of K plus, I have 1 equivalent. It'd be different if I had less than that, right? So we plug this in and we say 235 times 35, and then we're going to divide by 1,000, and then divide by another 1,000, right? So that's going to give us, let's see if I can squeeze that in there. It's going to give us 0.008. How many sig figs we got here? 2, looks like 2. 0.082. And then what are my units? What am I left in? Ooh, let's see, cancel them out. This is moles of K plus. And is that what we were looking for? We were looking for moles of K plus, and that's what we got. Okay. So K plus. Okay. And that's where I'm going to end. All right. I hope y'all have a great weekend.